Too much?
Too much.
Okay. All right, welcome to Too Much Chem. I'm Johanna Brown, an actual chemistry teacher, and today we are going to be talking about, today we're going to be talking about vapor pressure. Now, in order to really get a firm grasp of vapor pressure, you're going to need to have a solid understanding of lots of things. We're talking molecular geometry, molecular polarity, and intermolecular forces. So if you don't feel totally stable on those yet, go ahead and go back and watch those videos. But if you're ready to go, come with us. So first thing we're going to do is have a little horse race between three different substances. I've put them up here. We've got water, ethanol, and acetone. And so what I've done is I have soaked these pieces of paper in the different substances, and I'm going to streak them along the table, and we're going to watch them and see what happens. So if you're ready, make a bet, pick a horse, water, ethanol, or acetone. Let's see what happens. Okay, so when we watch these, acetone disappears almost completely. It's not even here anymore. We can see ethanol is evaporating before our eyes, and then water actually beat it up. And we all know that over time the water is going to evaporate, but it's definitely the slowest horse in the race. So if you picked acetone, you're a lucky winner today. But there has to be a reason behind the phenomena that we're seeing here. So let's just break this down by looking at the structure of the different substances that we looked at. So we have water, ethanol, and acetone here. So what do you think? I said we need to know molecular polarity, we need to know intermolecular forces. What do you think is going to cause these substances to stick together better or worse? Well, yeah, definitely polarity and therefore intermolecular forces. So let's just determine where there are polar bonds happening in these molecules, okay? So when we look at acetone, we know our hydrocarbons aren't polar, so those hydrogen-carbon bonds, those share the electrons really well, but we do have an oxygen-carbon bond here. So we're going to have the oxygen being a little bit more electronegative than the carbon, which is a little bit positive. So we have a slight dipole moment there. Okay, let's look at our ethanol over here. Again, we see this bulky hydrocarbon chain out over here, just two carbons though, no polarity here, but then we have an oxygen and a hydrogen. And you should feel pretty familiar with the fact that those create pretty intense dipole moments. So we're gonna see partial negative here, partial positive here, and that's something that can actually engage in hydrogen bonding. Okay, let's go to our last substance, water. So we have an oxygen bonded to two hydrogens. These are definitely some polar moments down here. It's going to be negative up here strongly, right? And there are all of these spots that oxygen can engage in hydrogen bonding. So when we relate this back to what we saw on the table, let's think about which one is going to stick to its compatriots the best. Well, it's the water, right? Because it's small, it's entirely polar, and it sticks together really well. When we look at ethanol, we have this group of hydrocarbons, doesn't stick together quite as well. Oxygen bonded to a hydrogen is going to engage in hydrogen bonding with other groups, alcohol groups, and so we'll see it sticks together a little bit better than acetone, but not quite as good as water. That was our second one to disappear. And acetone was the one that was the fastest. Let's look at why. We have these bulky hydrocarbon groups out here on the end that aren't polar, they can only do dispersion forces, and we have this little section in the middle that is polar. So it's hard for other areas of polarity to get in there and cause intermolecular forces to occur. So hopefully that makes sense. We're going to see acetone disappear the fastest because it has the weakest intermolecular forces. Water is going to be the slowest horse in the race because it sticks to itself really well. Okay, so intermolecular forces for water are high. Intermolecular forces for acetone are low. All right, let's look at this in terms of enclosed containers. So when your teacher asks you to talk about vapor pressure, what they mean is thinking about a closed container. So we're going to pour 1 liter of each of these liquids into our imaginary bottles up here and think about what would happen based on what we know about these substances. So we pour some water in. Do you think a lot of it is going to be in the vapor state or not a lot of it when water sticks to itself so well? Think about it. Hopefully you said not a lot. Okay, so I'll represent that with 3 water molecules. Okay, How about acetone? We pour some acetone in. We saw that it does vaporize very readily. It's volatile, that's another word for that. So are we going to see a lot of molecules of acetone in the vapor state in this closed container? Yeah. Okay, give me a second to draw these. Okay, now, what do you think about ethanol? Hopefully you understand ethanol is going to be somewhere in the middle. Doesn't have as strong of intermolecular forces as water, but it is stronger than acetone. Okay, so we'll draw some of our ethanol molecules in the vapor state. Okay, so vapor pressure. I said this happens in a closed container, and when we talk about vapor pressure, you really need to think about the pressure part of this. So pressure is caused by force over an area. So which of these three vapors is going to be causing the most pressure at the same temperature? Well, pressure is caused by these molecules colliding with the container. We're going to see the most collisions happening with acetone, so we'll see high vapor pressure here. Okay? And don't get yourself confused, because even though acetone has low intermolecular forces, because of that, it has high vapor pressure. Now we come over here to water. Not many molecules in the vapor state, so this is going to be low vapor pressure, and ethanol is going to be in the middle. And of course, I'm talking about these relativistically. It's all you should really be required to do in basic high school chemistry. So we've got to take a look at boiling point here. This is the other thing you're going to need to understand. So boiling point is that temperature at which we see things vaporize readily. It's when the vapor pressure actually equals the atmospheric pressure, but if you understand that that's the temperature at which something boils, you're good to go. Okay? So we need to think a high boiling point means high temperature at which something boils, and a low boiling point means low temperature. I like to think about it in terms of energy. So if something has a low boiling point, it means I don't have to put in a lot of energy to get it to vaporize. So when we look at our three options, which one do you think I'm going to have to put in the least amount of energy to get to vaporize? Well, hopefully you said acetone, this one that goes into the vapor state more readily. It's going to have a low boiling point. Okay, who's going to have a high boiling point? Well, hopefully you're thinking water. Water has a high boiling point. It takes a lot of energy to overcome the intermolecular forces that are holding those water molecules together, that cohesion, right? So we can apply this understanding to size of molecules, okay? So let's think about these two. We have some butane here, some octane here, and let's think about which one is going to have stronger intermolecular forces. And you might be saying to yourself, well, they both just have dispersion forces, right? Those are all nonpolar. But I want you to think about how much these could line up with other molecules around them. The shorter little butane can only line up so much, whereas the octane, this entire molecule, is going to line up in more spaces. And so it's going to have dispersion forces happening across here, all across here. Okay? So octane, being bigger, it also has slightly stronger intermolecular forces. Okay. How does this feed into what we understand about vapor pressure and boiling point? Let's see. So which one is going to have the higher vapor pressure? Which one is going to vaporize more readily in a fixed container? Well, think about it. Okay, I hope you said butane. It's smaller, it's easier to move, it has less mass, and it has fewer intermolecular forces. So it's going to become a vapor more easily. It's more difficult for octane. Now how about boiling point? Who's going to have the higher boiling point? Which one will take more energy to put into the vapor state? Well, I hope you think that's octane. It takes more energy. Okay? So to finish this up, I just have a couple questions for you to make sure that you really understand what's going on. So back to the table. So to check our understanding, we're going to compare methanol with methane. So first thing you should be checking for is what type of intermolecular forces are occurring in these molecules. Okay, so think about it. Do you see any polar bonds? Do you see anything that could engage in hydrogen bonding? Hopefully you notice that right here we have an oxygen bonded to a hydrogen. That will engage in hydrogen bonding with other methanols over here, right? Then we'll see some dispersion forces happening. Methane, just dispersion forces. And if you think about it, you probably have methane in the gas lines at your high school. So we know that it's already a gas at standard temperature and pressure. Okay, so we have stronger intermolecular forces with the methanol. Now, what does that mean for vapor pressure? Who's going to have high vapor pressure? Hopefully you said methane. Low intermolecular forces, high vapor pressure. Okay, who has a high boiling point? Well, that's the opposite of vapor pressure. High boiling point means you need to have a lot of energy to get this stuff to boil. So our answer for that one is going to be methanol. Okay, let's try one more. We're going to compare something else this time. Let's look. We've got some butane again versus decane. Okay, this 10 carbon hydrocarbon going on here, right? Just like our problem before, we only see dispersion forces happening, but we have slightly stronger intermolecular forces in decane as well as a larger molecule. Okay, so who has higher vapor pressure? Butane. Okay, good. Smaller, fewer intermolecular forces. It's easier to become a vapor. It's going to exert more pressure in a closed container. Okay, now which one is going to have a lower boiling point? Well, butane again, less energy to get it to boil. So that wraps it up on vapor pressure. I hope you learned a bit. Feel free to leave a comment or ask any questions, and make sure to subscribe to Too Much Chem.